Hi, everybody. Thanks for coming out. My name's Jason. I'm a committer on the Apache Cassandra project, and I'm an employee over at Apple. Just a quick note before we start. This presentation is not a contribution to the Apache Foundation. So let's dive in. So let's say that there's something big, new, and exciting happening in your life. Say you're going to get married or you're going to have a new baby. How would you go about letting everyone in your social circle know that this is going to happen? These days, what you'd probably do is probably put something up on Facebook, or you'd send out an email to all of your friends. But what you're probably not going to do is sit around at home just waiting for everybody to just send you that congratulations message. Instead, what's probably going to happen is your cousin will see your Facebook post and say congratulations. Then the cousin will tell the aunt will tell the uncle will not do anything. The aunt will then proceed to tell everyone else in the family, and so on. So essentially, everyone then knows that you're getting married. And so this piece of data has, this piece of knowledge has essentially been broadcast out through your social network. So there's a similar thing that happens inside of Cassandra. This is called the gossip subsystem. And that's what I'm here today to talk about. So first thing I'm going to do is talk about, well, what the hell is this thing? Then how is it actually used inside of Cassandra? Then we'll dive into the actual anatomy of the message passing, and how that resolves state. And then we'll see how gossip affects the rest of a running Cassandra cluster. So first of all, what is gossip? It's a broadcast protocol for disseminating data. It's decentralized and peer-to-peer. So what that basically means is that there's no centralized server that holds all the state that a cluster needs to talk to learn all the state that it should know about. It's basically a peer-to-peer where everyone is sharing information and replicating what is heard about other nodes from those nodes to new peer nodes. And in that style, it's called an epidemic broadcast. And what that means, similar to my potentially trivial example at the beginning, was I told one person, that person told another person, that person told another, and so on. And so this is epidemic in much the same way that biology works, where you have some infected organism, which infects another, which infects another, and so on. However, in computer science, this is actually a good thing that everything gets infected, unless it's a security worm. So gossip is a fault-tolerant kind of a protocol, because once that knowledge has been disseminated across a couple nodes, if one or two or even most of those nodes go down, still a few are infected, and they can continue broadcasting out that information to the rest of the cluster. And gossip is an efficient and reliable broadcast protocol. It's got a pretty minimal overhead in terms of the way that the mechanisms with which we broadcast these messages, and it's pretty lightweight. So back in the 80s, there was an excellent paper called Epidemic Algorithms for Replicated Database Maintenance by Demers et al. Basically, they built a system called Clearinghouse, and they were the ones to really first talk about this whole concept of epidemic broadcast and gave us the language to talk about this style of replication. Excellent read, by the way. So let's look at a quick example of how this actually works. So say you've got a node here. Let's say you've got a 16-node cluster, or 16 anythings. And this first node has some piece of information it wants to share. It then invokes another peer, and now that peer has the data. Both of those peers invoke two more, and now 4 out of the 16 are infected. Can you guess what's going to happen next? Those 4 are going to call 4 more. They now have the data. And lastly, those 8 now call 8 more, and that has it. And now the entire cluster has that data. So this is just one node talking to one other node on each round, and so it's a base 2 log, a log base 2 kind of operation. You can have a wider fan out. So instead of talking to just one peer, you can talk to 5, 6, 10, whatever you want. But there's extra costs in the networking involved and sharing. So why do we use this in Cassandra? Probably the more interesting questions. So we use it to reliably disseminate node data amongst peers, node metadata across peers. And those types of metadata are the cluster membership, basically what nodes are in this cluster, heartbeat, and the node status and other metadata points about a given node. And each node maintains a view of all of its peers in the cluster, including itself. And this information is, of course, much as I just described, disseminated out in an epidemic sort of fashion, each node talking to another node, and then spread out. Now that I've talked about what what we actually use it for in Cassandra, let's take a quick second to talk about what it's not used for in Cassandra. It's not used for streaming, repairs, reads or writes, compactions, hints, CQL, or any other fancy things, and it's also not responsible for my morning caffeine. So just just very important to delineate what gossip actually is not doing, helps to box in the conversation. So let's dive into the details. So there's 3 main data structures inside of the gossip subsystem. I'm not going to talk so much about code or dig into that, but talking about the data structures helps to structure the discussion. So there's a heartbeat state, an application state, and an endpoint state. Inside of each node, the endpoint state is more or less a wrapper around a heartbeat and a collection of application states. And inside of each node in Cassandra, for every peer node in the cluster, there's a map of endpoint states for each peer. So the heartbeat state, there's 2 pieces of information in this. There's a generation and there's a heartbeat. The generation is essentially the timestamp of when the process was launched. It's largely immutable throughout the Cassandra process during the lifetime of the process. But there's some special tricks that I cannot talk about at the very end about why we would actually violate this. So the heartbeat then is just a periodically updated, monotonically incrementing value. Now the layman's definition of that is basically just it's an integer that we update every second. And the reason why that's important is because it's a heartbeat. You want it to keep being updated, and updated, because if the heartbeat isn't updated, it might be dead. So application state. It's essentially a tuple of an enum name, some value, and a version. And these are contained as a map inside that endpoint state collection for each peer in a cluster. So I will talk about enum names in a second, but then the version is essentially a versioned value for that metadata point. So every time we increment the value, we'll also increment that version number. That way it'll help with comparisons later on to help assure convergence of all this data. So the enums of this application state. There's probably about a dozen or so inside of Cassandra, but I've only put up the most common ones up here, or at least the ones I find to be the most interesting. So data center and rack, pretty straightforward. You want other peers to know, just where you are physically or where you are logically. Schema, it's just a schema ID so that we can compare if 2 nodes are out of date and they can exchange it, if it finds it out of date. The load is basically just raw disk space used by a node, and it's updated every 60 seconds instead of every peer. Severity being a rough heuristic of I/O pressure on a node, like I/O weight stats, compaction, and dynamic snitch measurements. And where that becomes interesting is looking at the scoring and ranking of peers with the dynamic snitch, which we'll talk about at the end of this talk. And the status enum. So status is actually pretty important and probably one of the most important states of these all of these. So bootstrap, when a node is launched, it's going to set its state to bootstrap, and then it'll gossip that out. It doesn't last very long, assuming that the node has been launched before and it has data. But if it's a new node, it'll stream information to itself, and then it'll move out of bootstrap. Hibernate is a very short-lived thing as well. It's only if you're actually replacing a previous node. Not too important. Normal is, of course, the state that every node wants to get to. It means that it's a normal part of the cluster and is behaving as it should. Leaving and left have to do with decommissioning a node out of a cluster, and removing and removed have to do with when you actually remove a node that you no longer have physical access to the machine to run decommission on that, so you have somebody else essentially remove it from the cluster. The thing that's really important about the status is that this is the status that a node has declared about itself. It's not an evaluation by any other node. So this is what a certain node says that I'm up, I'm bootstrapping. It says I'm bootstrapping or I'm normal. Up and down is a rather different concept that we'll talk about soon. So let's take a quick little example of just the gossip or metadata points out of a small, tiny 3-node cluster I launched on my laptop. As you can see, I've got nodes A, B, and C. The generation is slightly different. The generation is more or less a timestamp since in milliseconds since the epoch. And since I launched it on my laptop with a script, they all pretty much launched at the same time, the only difference being the last millisecond. The heartbeats are slightly different, but that's OK. They don't have to be exact if they're launched at the same time. If you'll notice, node A has a value that's 2 less than the other 2. It could be that node A went through some stop the world garbage collection pause for 2 seconds and wasn't able to update that heartbeat because it was in the stop the world pause. But ultimately, the values lining up really doesn't matter as long as it's an incrementing value. That's the most important thing about the heartbeat. And status, they're all in normal. And the second value in there is just essentially the first token that node owns. Not too much interesting. And then the rest of the values you can see are the same. So let's dive into the actual messaging of gossip. So it all revolves around a gossiping round. And every node, every second, starts a new round of gossip. Now, there's nothing that coordinates every node saying, hey, go out and gossip. Every node, because this is a decentralized kind of system, every node just starts this new round by itself. It's got some timer tasks that kicks off, and we start a new round. And what we do is we select between 1 to 3 peers to gossip with. We'll always pick a live peer, if there are any in the cluster. We'll probabilistically pick a seed node to talk with. And we'll probabilistically try to call an unavailable node. So a node that we've previously labeled as down, we'll then try to reconnect with. And we just probabilistically do that rather than always doing it because because A, for the seeds, we don't just want to pummel that with gossip traffic. And for the unavailable nodes, you don't want to flood the network with packets that are just going to be dropped on the floor. So let's dive into the messaging. So Cassandra's gossip messaging is very similar to the TCP three-way handshake. In the three-way handshake, you have a SYN, an ACK, and a SYN-ACK. Inside of the gossip, we have SYN, ACK, and ACK2. Now, why it's called ACK2 rather than SYN-ACK, it's an excellent question that I don't know the answer to. So if you'll notice, it's got 3 messages in it. With the broadcast protocol, we could just ship out 1 message and be done, and then let all that information just eventually percolate out through the cluster. By having 3 messages for each round of gossip, it allows us to add in a degree of anti-entropy into the gossiping protocol. That way we can get to convergence much faster, so that the 2 nodes have the same data shared between them, which is of course more or less the point of this gossip. So, SYN. The node that's starting the round of gossip, I'm going to call it the initiator. Basically, it calculates a digest of everything it knows about the cluster and then sends that off to the peer that it selected. And it's basically, the digest is a tuple of the IP address of a node in the cluster, the generation that node thinks it is, and the heartbeat version. Once the peer receives that SYN, it's going to do a diff against what it thinks the cluster is, and it's going to create a new message called the ACK and send that back to the initiator. The ACK has 2 components. The first one is a set of updated metadata that the peer has that the initiator doesn't. And then the second part is a digest of the nodes that the peer needs the updated information for that the initiator has that the peer needs. So essentially, they're exchanging data. So if you've got updated information, I want it, for some things, but for other things, I know I have updated information, so I'll send it over to you. Then the initiator, once it gets that ACK message, it'll apply all the local diffs, and for the digest that was in the ACK message, it'll produce another set of diffs, create an ACK2 message, and send that back over to the peer. The peer, of course, on receipt of that, gets it, applies it, and the round of gossip is done. In all, it's actually a pretty lightweight operation and not very resource intensive. So if you remember, inside of those app states, and there's this generation and heartbeats, these are all integers. And I mentioned that these are all incrementing values. So let's talk about how, inside of a round of gossip, how we actually reconcile who's out of date and who has a more updated value. Cassandra's gossip anti-entropy is based upon the Van Renesse paper, Efficient Reconciliation and Flow Control for Anti-Entropy Protocols. A big, long title, but it's essentially how do we make data converge fast in a gossiping kind of system. It's also nicknamed the scuttlebutt paper, as you can see in my poor handwriting that I didn't erase. So the AppState reconciliation has essentially three levels of precedence: the generation, the heartbeat, and comparing the app states, if you remember, those individual metadata points based upon that version that I mentioned. So let's take a look at an example of how we can reconcile the data. So in this example, I've got a 4-node cluster, nodes A, B, C, and D. And this is a round of gossip between nodes A and B. Hope this is at least semi-legible over there. But so first, they're going to compare the metadata about A. The generations are the same, 1, 2, 3, 4. The heartbeats, however, are different. A, since it is the owner of that data, thinks that its heartbeat version is 994. B thinks that the heartbeat is 990. Obviously, 994 is more current. So therefore, at the end of this round of gossip, B will update its notion of A's heartbeat to the value 994. For node B, you'll see that the generations are again the same. The heartbeats are different in this case. So A thinks it's 10. B says it's 17. However, more interestingly is the status is different between the two. A currently thinks that B is bootstrapping. And you'll see that I put the number 1 in braces just to indicate the version that it's at. B, however, has now entered the normal state and has updated that status to normal. And it's also incremented the version to 2. So how we actually compare these application states is just strictly based upon that version number. We don't actually try to compare the values to see which is bigger or whatnot. It's always based upon that version number. So in this case, 2 is bigger than 1. At the end of this round of gossip, A will think that B's status is now normal with the version of 2. Now, if the version on B was, say, 7, and A still knew about version 1 of that value, we actually don't care about any of the intermediary states. So 2, 3, 4, 5, and 6, A won't care about. We just care about the latest value. It doesn't care about any of the intermediary values. So looking at node C, B totally doesn't even know that that node exists. So in this case, B will just take anything B will take anything that A has to say about C, and after this round of gossip, B will now know that C exists and is part of the cluster. And finally, node D, the generation is different. A thinks that the generation is 2222, and B says that it's 3333. In this case, node D has bounced. It was restarted, and now has an incremented generation value, which means that A will take anything that B says about D because D was bounced and it has a potentially new set of metadata points. So at the end of this round of gossip, A will take everything that B has about node D. So let's just briefly summarize the message passing here. So each node independently begins a new round of gossip every second. And it selects 1 to 3 peer nodes per round. And it's always going to pick a live node, probabilistically a seed node, and if there are any unavailable nodes, we'll probabilistically pick a unavailable node as well. And it's 3 messages per round. And the other thing to note is that it's always going to be a constant amount of network traffic. So because we're always going to broadcast the same number of nodes in that initial digest, and passing the metadata back and forth in the ACK and ACK2 is going to be pretty much constant across all the rounds of gossip, across all the nodes in the cluster. So because of gossip itself won't necessarily cause any network spikes. It's always going to be a pretty flat, constant rate of network traffic. And the reason I bring this up is that sometimes I've heard complaints about things like a gossip storm inside of Cassandra, where certain network events trigger and it just happens to get blamed on gossip. That's usually almost never the case. Gossip is a very constant trickle in the background of your cluster. Of course, if you get into clusters of 10,000 nodes, the packets passed back and forth are inherently going to be larger. But then again, you've got a cluster of 10,000 nodes. The reason why you have a cluster that large is because you have that much data, and you're probably already maxing out the network bandwidth anyways. So gossip really isn't going to be the cause of that. However, when gossip does choose to mark a node up that was previously down, what could be happening is that if there was one node down in the cluster and then it comes back up and all the nodes see that it's up, they're probably going to start streaming hints and things like that over to that node that was down. And that's probably more likely the cause of what is frequently called a gossip storm. Gossip didn't necessarily cause this, but a practical effect inside of Cassandra, seeing that a node is now up, means that we're going to start streaming data over to that peer node. So I want to spend some time talking about the practical implications of gossip, continuing on the previous thought. So there's some questions that will be really good to answer. And those are, who's in the cluster? What other nodes are there in this cluster? How are these peers judged up or down? And more importantly, what does up and down really mean? I'll tell you, it's actually not what you think it is. When does a node stop sending another node traffic? Good question. When is one peer preferred over another? Closely aligned with the last question. Then the last thing we'll talk about is, when does a node actually leave the cluster? And when does it doesn't? And what happens when it doesn't leave the cluster and it's supposed to? So cluster membership. We kind of talked briefly about this in my a discussion of how when we talked about the reconciliation between gossip messaging. So when a node a node starts up, it basically needs someone to start gossiping with, right? It's the whole point of gossip is to have someone to talk with. Well, if you're starting up, and you need to know the address of someone to talk to. But how do you know what that is until you actually gossip with someone to find out what the other addresses are that you should be gossiping with? Well, if you've ever dealt with the Cassandra YAML file, there's a seed provider. The most common example is the simple seed provider, which you just give it a hard-coded list of IP addresses. There's a couple of other seed provider implementations that essentially provide a list of host names or IP addresses. So that new node that comes up gets this list of seed addresses and starts gossiping with one of them randomly. And through that, it's going to learn about all the other peers that are in the cluster. And then, because it knows about all the other peers in the cluster, because of that first round of gossip, it can now gossip with pretty much everyone else in the cluster. Then, of course, for every other new node that comes up in the cluster, lather, rinse, repeat. And so that's how we essentially grow a cluster organically by disseminating all this cluster membership information inside of the gossip messages themselves. So, up and down. The measurement of up and down is specific to a node itself. We never, 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 never broadcast to any other node that I think that another peer is up or down. It's always local to me. And how we actually determine that is based upon the heartbeat that I mentioned earlier. And how I actually get updates, how a node actually gets updates about another peer's current heartbeat value doesn't necessarily need to be communicated directly to me, but it can come indirectly. So if I have a 3-node cluster, nodes A, B, and C, A can gossip with B, and B can gossip with C. So there's all normal communication between those three. But let's say that A can't communicate with C for whatever networking partition problem that might exist. But B is still getting all those heartbeat updates from C. Because A knows that B is up and legit, and because A is also gossiping with B, A will get the heartbeat updates about C, even though A can't talk to C. So therefore, A will still think that C is up, even though all the network traffic between A and C could be completely dropping on the floor, packets are timing out, no ACKs, no SYNs, no nothing. A is still going to think that C is up. So how we actually determine if something is up or down with that heartbeat is another component inside of Cassandra called the failure detector. Briefly, it's based upon the fee accrual failure detector paper. And at the end of the day, it's just a glorified heartbeat listener. And what we do is every time we get an update about a peer's heartbeat, we record a timestamp. Actually, what we record is the diff of the timestamp between now and the last time we heard an update. And we keep a backlog of those updates, and we generate a mean value. And then we periodically check all the peers in our endpoint state list that I mentioned earlier. And we check that list and the backlogs of every node to see if we've heard from that node recently. And we generate a score, and if it's been too long that we haven't heard from that node, we'll actually mark it as down. So for the general purposes of this discussion, the only thing inside of Cassandra that can mark a peer node as down is the failure detector. And that's based upon receiving those heartbeat updates. Almost nothing else will mark it down. Conversely, only Gosper can mark a node, the Gosper, the primary gossip class, sorry. That's the only component that can mark a node as up. There's a couple minor details, but nothing that should interest anybody else besides coders inside this thing. So what does this notion of up and down really affect? How does it affect your cluster? So it does not affect writes, because we always want to send writes to the target node that it needs to go to. Whoever owns a certain range for a key, we always try to shove it over there. And if we fail to get an acknowledgement or a receipt from that node, we'll actually store that up as a hint. Pretty common in Cassandra. If a node is down, we won't send any read requests over to those peers because we'll assume it's dead and there's nothing good that can come from it. Similarly, we'll treat the gossiping to that node differently once we mark it as down. It'll be in the dead state, and technically it's an unavailable node at that point, so we won't always try to gossip with it. Or if you remember from a few slides ago when I talked about which peers we choose to select from, clearly it's down, we don't think it's live, so we won't pick it from that list. But we might probabilistically try to talk to it because it's an unavailable node. And lastly, any open repair and stream sessions are terminated. Now, probably because you haven't been getting those heartbeat updates, the node is down, or there's some network partition, and probably the socket connections are dead, or nothing is being ACKed or whatnot. So basically, all we do is terminate the sockets and close any memory sessions just to clear up space. So that's great about the heartbeat and all, but what really happens if that peer is running really slow? Everything's timing out. Do we ever mark it as down? No. However, we're going to try to avoid that node. And that brings in another component called the dynamic snitch. And basically what it does is it records latencies of whenever we send a peer node read requests. And basically what we do is we keep a rolling window of latencies as we've talked to that foreign node. And essentially we rank them based upon scoring. And we re-rank them about every 100 milliseconds. And the scores are reset every 10 minutes. The reason why we reset the scores every 10 minutes is that allows nodes that maybe we're having some long GC period for whatever unfortunate reason to actually get re-ranked correctly where it should be in a list. So that if it normally is a faster responding node yet had some heavy I/O or some heavy garbage collection going on, it can then be re-ranked. So let's switch a little bit and talk about how nodes actually leave a cluster. So there's a couple different mechanisms. One is to use the node tool decommission feature. And for that, you actually need to log into the actual node that you want to exit the cluster and run node tool decommission. What happens is that node is going to change its status to leaving and then broadcast that out. It's then going to find the peers who should now own the ranges that it has and stream the data over and then send any hints over as well that should be played to any peer nodes who might be unavailable at that time. Then after all that activity is done, it's going to change its status to left, and it's going to set an expiration time. The importance of the expiration time, which is currently hard-coded at 3 days, is that hopefully within the span of 3 days, you've broadcast to every peer in your cluster that, this node is dead, forget about it after 3 days. After that 3-day period expires, then there's about an extra 5-minute window into which we quarantine that node just to make sure that everybody's moved it into the quarantine and then we'll just, then every node will basically just toss it away after that 5 minutes, and it will never, and it should be hopefully gone forever. The next way of removing a node is removenode. Once again, it's another node tool command. However, removenode is when the node that you want to kick out of the cluster is no longer available for you to log in and run decommission on. So you had to go to some other random node in the cluster and execute this. So that initiator is going to set the status to removing for that peer who's gone. And then every node is responsible for rebalancing the cluster. So they need to figure out what nodes now own which token ranges and then stream some data over to them. They'll each all then delete any local hints they had for that node that's now gone, and then finally notify the coordinator or initiator that they're done with all their actions. At the end of all this activity, that coordinator is going to set the status to removed, and once again set another expiration time so that everyone can drop that node's information after 3 days. Replace node, this is something we commonly did in EC2 for just replacing a node that's no longer available and reusing its token. We perform what's called a shadow gossip round, which is basically kind of like a mini gossip round. Basically what we want to do is probe the cluster to see what other nodes are out there. Because we're trying to replace somebody, let's see if it actually was in there and find out the tokens that it actually owned. So it's called a shadow gossip round. It's basically just a SYN and an ACK without any ACK2. Because clearly the node that's trying to replace somebody doesn't know anything about the rest of the cluster. It's just trying to grab information from the live nodes. So we take the tokens and the host ID, then we check that the owner actually is dead and isn't still actively gossiping in the cluster. Then we just stream the data from any live nodes to ourselves. So that's what happens when everything goes right when you want to kick a node out of the cluster. What happens when things don't quite go so right and you remove a node, but yet it kind of hangs around in your cluster for days, weeks, past that 3-day period? A lot of you, I see nodding your head, kind of knowing what's coming. So we assassinate that damn node to get rid of it. So there's a JMX command called unsafe assassinate endpoint. A little bit unfortunate with the naming of unsafe, but it should be used with caution. But it basically forces a change to a peer. So similar to how that remove token, the remove node command works, you invoke it on a node because that original guy is gone, and you give it the IP address of that previous node. And what we do is we force that generation to be updated, and we force the status to be, I think, dead. Then that gets gossiped out as normal, and hopefully after 3 days, it will effectively disappear off every node in the cluster. So, takeaways. Epidemic broadcast protocols provide a resilient and efficient mechanism for data dissemination. Basically, I tell you, you tell a friend, you tell another friend. At the end of the day, it's just rumor mongering, just sharing information all around in kind of a decentralized manner. And inside of Cassandra, we use it for peer discovery and metadata propagation. That way, everyone eventually comes to kind of an agreement, even though that it's never quiescent because that heartbeat is always updating. We always have some kind of general notion about what the status of the cluster is. And at the end of the day, really, this whole thing isn't that mysterious once we just peel back the layers of the onion to figure out what it's really doing underneath. And with that, thank you, and I'll open it up for questions.